Good afternoon, everyone. In this recorded presentation, I'd like to describe some of the models that we have been developing, in particular looking at the situation where drilling, maybe from a geothermal project or some other scientific experiment, intersects a shallow magma body and some magma enters into and travels up the geothermal borehole. I've been doing this work with a colleague at the University of Canterbury, Craig McConaughey. So we'll start with a recap of a few instances where this has actually happened before. One of the well-documented cases is from the Puna geothermal field in Hawaii, which has been in the news. Most recently in 2018, there was a fissure eruption here that impacted a lot of the geothermal field itself. However, in 2005, some drilling encountered a magma body at a depth of about 2.5 kilometers. So this is the well KS13 here, and you can see they were able to essentially characterize about 1,000-degree dacite melt down there. And what was really interesting was they noticed that the melt itself flowed into the borehole, and it flowed up the borehole about 5.5 meters in a few minutes. That's the best I was sort of able to get in terms of a timing, as reported in the paper that describes this TEPLO. So you can calculate a little flow rate if you know what the dimensions of the borehole are, and it's pretty low, about 1.4 times 10 to the minus 3 meters cubed per second. And to put that in context, the Kilauea eruption itself that covered this geothermal field was about 100 cubic meters of magma a second. And the indescribable volcano in Iceland that was producing all the nice drone shots last year, that was about 6 cubic meters a second. There has been, of course, a very well-known intersection in Krafla geothermal field in Iceland. So here, drilling of IDDP-1, which was intended to go down, I think, about 5 kilometers, instead ended up encountering another dacite magma at about 2 kilometers. And there, if you look at the drilling logs, and when they pulled the drill string up and dropped it down again and encountered more disruptions, they found that the magma had flowed probably about 7.5 meters up that particular borehole in about 3 minutes. And again, if you do some calculations, you'll find that it has a very similar kind of flow rate to that KS13, probably because it's a reasonably similar magma, in this case about 3 times 10 to the minus 3 meters per second. Now, that's not the first instance of magma in a geothermal borehole in the Krafla region. The Namafiel geothermal field to the south in the 70s actually had an eruption out of one of their geothermal wells. This was during an eruptive period called the Krafla fires, and what was known about that is essentially a basaltic dike that started moving into this geothermal field during that eruptive period. It intersected the borehole at about 600 to 1,000 meters depth, and then it occurred at midnight, so records are a little sketchy, but it erupted out of this. There is these sort of grainy pictures of the eruption column with some sort of inferred ascent velocities of about 20 to 30 meters per second. And then the next day, this is that same well venting steam now, and I believe they repaired it, and it produced for another few years afterwards. And then as well, we have the Menengai geothermal field in Kenya, and there were a couple of intersections inferred with magma here. That's mainly from cuttings returns that showed chilled, very fresh glass that you'd really only get if you had intersected a magma body. So that was, again, at a depth of about 2 kilometers, but there's no associated rise velocities for this case. So we set to work trying to develop just some simple models to describe, all right, if you've got magma entering a borehole, what is the likelihood that that magma could potentially reach the surface? Obviously that happened in Namafiel in 1977, but it didn't happen at Puna or at Krafla. And we modeled the problem as a thermal survival one. Basically we say, look, magma can reach the surface if it can stay in a non-crystalline state all the way as it passes up the borehole. So here we have a magma body at some depth, Z, and we'll imagine that drilling kind of intersects it and the magma rises up to a height H in some time T. with some kind of overpressure in the magma, delta P, that's related to buoyancy or whatever else you want to ascribe it to. Now, the best model we have at the moment for flow of magma in a cylindrical geometry is just basically fluid dynamics in pipes, something called Hagen-Poiseuille flow. And using that, we can calculate both a magma rise velocity, which is the highest in the middle of the borehole and drops to 0 at the outside, and depends on things like pressure gradient and viscosity. And if you take that magma rise velocity and integrate it with depth, you can get an ascent time. So this is how long it takes the magma to reach the surface. And it depends on things in the way you might expect. Lower viscosity magmas have less drag, and so they reach the surface quicker. If you get a shallower magma body, or if you have a much wider borehole, or if you have a larger overpressure at the base that's pushing this magma up, all of these things contribute to a smaller number on the left-hand side, basically the magma reaching the surface quicker. So that's one part of the thermal survival problem. How long does it take the magma to reach the surface? The other part is the freezing. Can we freeze that magma? Do we have enough time to freeze it before it reaches the surface? And there's two models we've considered. One is a radial freezing model, so heat diffuses out into the rock. You can solve that problem numerically, and we find it depends on, there's a rather tricky integral that you can find in the paper and see how we solved it. But more importantly, things like the latent heat of crystallization, how much heat you have to pull out of the magma to turn it into crystals. Heat capacity, various temperature differences between the magma and the rock that will drive that diffusion process. And the thermal diffusivity appears in this integral here. They also all depend on the radius of the borehole. The second model for freezing this magma column is the formation of a plug. So this is the idea that you have some cold fluids potentially in the borehole, drilling fluids perhaps, and they are cooling the front of the magma down as it's pushing upwards. And if you grow this thing large enough, essentially you'll increase the frictional drag of the plug. And when that's large enough to overcome the pressure of the magma column, then you'll cause this thing to stop. And you can solve that as well, and it turns out that the plug formation time depends on various things like density differences and, again, latent heats of cooling, thermal conductivity, all various things that we can, in theory, find some numbers for and start estimating. Very good. So those are the models. What we've done is taken those and said, all right, well, how do those various timescales change for well bores of different radii? And that's what I'm showing along here. So the first thing I'll show you is the ascent time of a basaltic magma. Basalts have much lower viscosity than rhyolites, which are the other end member. So a basalt, for example, is what erupted out from Namafjall. And here, if you chuck in some reasonable estimates for viscosity for various depths and overpressures, then you end up with anywhere from minutes to days or weeks for very small boreholes to get these basaltic magmas up. And we find that's probably a bit longer, quite a bit longer than the 45 seconds estimated for Namafjall. But there are quite a few unknowns about that eruption, and possibly the magma could have entered the borehole a lot earlier. The onset or the arrival of earthquake activity suggests maybe almost up to 2 hours beforehand, and that would place us in a fairly reasonable range consistent with the model. The Puna well, and in fact also the Krafla IDDP magmas, they're daceites, so we can calculate, we have their ascent velocities actually, and we can find, given a 5.5 meter ascent in 200 seconds, translates to about 1 year to reach the surface for those magmas, and that's pretty well in line with what we're seeing for those potential viscosities for that kind of magma, and it's the same at both Puna and Krafla. One thing that's quite interesting though is the arrest time. Certainly at Puna, the freezing occurred much more rapidly in 200 seconds, and that's a bit quicker than we would expect. So it suggests that the cooling here, if it is by plug arrest, is a lot more efficient than what we have been modeling. We're continuing to look at why that might be the case. Radial freezing, I'll just touch on this briefly, really to say that this isn't really a credible mechanism. It takes much longer to freeze magma radially than it does to form a plug under reasonable parameter ranges. So we're not dealing too much with this mechanism, much more. So there we go, just compiling all of those together, and this is the figure in the paper. One of the questions we sought to ask and answer are essentially what are the conditions under which you'll get a magma up to the surface before it freezes. And we find for a basaltic magma, you need to be reasonably large in terms of your borehole to achieve that. We're talking pretty large boreholes here of 0.4 meter radius. For a rhyolite, because the viscosity is so much higher, again, you're talking about really unrealistic sized boreholes. It's just not going to really end up, at least by this sort of mechanism of slow creep of the magma up to the surface. So this work is ongoing. We're looking at other sort of more exotic models that could explain different aspects of the physics. Things like, you can check the paper if you're interested in a lubricating annulus model that allows volatiles to exsolve into the outside and really accelerate the magma up there. Explosive decompression is something we're going to look at in the future. Generally speaking, though, early indications are that you need very particular conditions to get magma to the surface by the mechanisms we have considered here. And even then, you're going to end up with very low flow rates that probably can be managed with interventions. With the caveat there that we haven't considered other sort of eruptive mechanisms like decompression, explosive decompression, that would be very much more disruptive and dangerous.